Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 1st, 2025, about 3 days ago. This paper tackles dense feature matching, which is the challenge of finding corresponding points between two different images of the same scene. And the new method here is so robust, it even works on pairs of regular and infrared photos. The paper is titled, Learning Dense Feature Matching via Lifting Single 2D Image to 3D Space. And as we'll see, the results are really impressive. Alright, so this first figure really lays out the core idea. On the left, we see the traditional approach, which uses small, clean sets of multi-view images. The problem is, these are hard to collect, which limits the model's robustness. But on the right, we see their new two-stage framework. It starts with millions of diverse, single 2D images. In stage 1, it cleverly lifts these into 3D space by estimating depth. This process teaches an encoder, the part of the model that analyzes the image, to be genuinely 3D aware, and stage 2 then uses that powerful encoder to train a robust feature decoder. Okay, and this figure gives us the full architectural overview of their two-stage framework. Stage 1, at the top, is all about training that 3D aware encoder. It uses multi-view images to build what they call 3D Feature Gaussians, which are a way to represent an object's features and shape in 3D space. This process teaches the encoder to understand geometry. Then, in stage 2, they freeze that smart encoder and use it to train the feature decoder. This decoder learns to find dense matches between the diverse, synthetic image pairs we just talked about. So, where do they get all those single 2D images for that stage 2 data pipeline? Well, this table details the huge variety of real-world datasets they pull from. We're talking over 500,000 images in total, from datasets like Suco, new scenes, and cityscapes. And the diversity of scenes is really key here. Everything from common objects in urban streets to low light, underwater, and even aerial views. This sheer breadth of training data is what gives their final model such incredible robustness and the ability to generalize to new, unseen scenarios. Moving to the results, this table really shows the payoff from using that diverse training data. It compares their method, L2M, against others on the zero-shot evaluation benchmark. Zero-shot means testing on completely unseen data, a true challenge of generalization. The main score is the area under the curve, for pose error under 5 degrees, which measures how accurately the model estimates the camera's position. A higher score is better. In looking at the mean column, their L2M method achieves the highest score, 51.8%, outperforming all other dense methods. This next table then gives us a look under the hood with what's called an ablation study. Basically, they break their model down to prove which parts are doing the heavy lifting. The top row is their full L2M model. The middle row removes that special 3D aware encoder from stage 1, and the bottom row removes both that encoder and the diverse synthetic data from stage 2. And as you can see across both real-world and synthetic datasets, the scores consistently drop with each component they remove. This really proves that both stages are critical. Alright, to wrap things up, what this L2M method really proves is the power of its two-stage design. The key takeaway is how it generates its own massive and diverse training data by lifting single 2D images into 3D space. This allows it to learn dense feature matching, which is the complex task of finding a corresponding point for nearly every single pixel between two different images, with remarkable accuracy. And it excels at zero-shot generalization, meaning it performs exceptionally well on completely new datasets it has never been trained on. That's all for this week. I'm Alex, and this was the AI Research Roundup.